Example 4, for each of the following, find the general solution by algebraically manipulating the differential equation. First to the separable form. So don't forget, you always have to break this thing up into its separable form. So get all the y's and dy on the same side and all the x's and dx on the same side. Let's see. Boy, we got a problem here. We're going to have to do a rewrite. Because right now, I could natural log both sides, right? And that would get that x and that y down. But I'd be up a creek because now my dy dx would be trapped inside of a natural log, which means I couldn't move the x dx to the other side, or I could move it first and try it, but then my dy would still be trapped inside, so I couldn't really integrate. So I would recommend a rewrite here. And this is going to go back to your log properties and exponent properties that we've done. Well, probably algebra 2 and on. I think we might hit it a little bit. Yeah, this is an algebra 1. This is for sure an algebra 1. So think if you can remember e to the x minus y. How can we rewrite that? What I do here, I can never remember, so I go and I make a simple problem. Like e to the, 7 minus 2, okay? Now, how could I rewrite that using multiple e's? So like e to the 7 and an e to the 2. How would I have to combine them? And hopefully you remembered that when it's a plus, you need to combine these with a multiply. And when it's a subtract, they get combined with a division. So I can now rewrite e to the x minus y according to this little property that we found up here. I can rewrite this as e to the x over e to the y. And now that I have these, now it's pretty easy to separate and go. So I would encourage you to try to pause and try that on your own. Let's see how you did. So I'm going to bump this over here. I'm going to bump this over here. So we now have e to the y dy equals e to the x dx. This is 1 point. Just getting this thing in its separable form. Now I'm going to integrate both sides. And so what's the integral of e to the y? Well, beautifully, it's e to the y plus c, but I'm going to put that plus c on the other side. The integral of e to the x is e to the x, and then I've got to make sure that I don't forget the plus c somewhere. Now remember, our goal here is to get the general solution. That means to get y by itself. So what would get that y down from e to the, I'm going to natural log, and I'm going to natural log. How you write this matters. So you need to write this as y equals natural log of the quantity e to the x plus our constant. So we can't distribute that natural log. We also can't cancel the natural log and the e to the, because this stuff's connected by add. Our properties for our exponential properties involve division mult. All right, let's see how clever you are. Why don't you try the next one? See if you can figure out how to get x and y on opposite sides. So obviously we have to do a rewrite here. So I'm going to now push this to the other side. dy dx is equal to x plus x y squared. So I'm going to want to multiply both sides by dx, but I want to clean this up first. I want to try to separate these because right now I've got a problem. I've got too many x's, and if I divide by y, it's going to mess this one up. So I want you to look at this and think about what we can do with that guy. Well, hopefully you thought dy dx is equal to, I can take out an x. So I can factor out that common term. And now I can do a little multiply. I'm going to multiply this over here, and I'm going to divide this over here. So now I'm going to have 1 over 1 plus y squared dy equals x dx. Okay, now I want to integrate. And as we integrate, this should be ringing some bells. If you're an AP test taker, this really should be ringing some bells. If not, if you're one of the non-AP test takers, go back and look at 4.1. There's the second page of 4.1, he has a bunch of antiderivatives in there, and it turns out that this antiderivative is arctangent. So this turns out to be arctangent of y equals, and then the integral of x is x squared over 2. And you must put your plus c in here because, oh, I forgot to write it over here. I like to write it. This is a general solution, not a particular solution, because it still has c. Okay, now this is not yet in its general solution form because we don't have y equals, so we got to kill off arctangent. And what kills off arctangent? Hopefully you remembered that tangent does, and make sure that you tangent the whole side. So we get y equals the tangent of x squared over 2 plus c. And again, I like to write myself a little note. This is a general solution, not a particular, because it still has the plus c. All right. Find the differential equation, blah, blah, blah. Find the general solution equation first. So I'm going to give you a second. I'd like you to try to manipulate as best you can. Let's see how you did. So I'm going to bump the x, definitely bump the x to the other side. So I now have y dy dx equals x. And then now I just need to get this dx to the other side. So I get y dy equals x dx. That's not too bad. And then I can integrate. I'm going to draw some arrows here since we have so much nice room. Rare we get this much room to work on a problem in Corpy's notes. So I would integrate now both sides. The integral of y is y squared over 2, which is equal to x squared over 2. Don't forget your plus c. You have to at least write one of them. Then I can multiply everything by 2, so I would get y squared equals x squared plus 2c, but we don't know what c is anyway, so we can just leave that as c still. Now look, this is not a general solution until you get y by itself. So who's keeping y from being by himself? I'm going to square root is on fire. We don't need no water, we just need a plus or minus. Box it in, put it up on your fridge. I'm going to leave myself another little note that this was a, I don't like that color, general solution. Oh, zoomed in too much. General solution. Part B says find the particular solution that passes through 0, -4. So I'm going to take my equation and now I'm going to try to solve for C based on this initial condition. So y is -4 plus or minus x is 0 plus c. Who's farthest away from x on the same side? So I can square 16. That's 0. So 16 equals c, right? Game over. C equals, not quite, because when we go back, so now I have y equals plus or minus x squared plus 16. And I have to make sure, look, this is not a particular solution yet because I don't know which one of these I have to select. So what you want to do now is you want to plug in and see which one works. So let's say I put -4 in there. -4. No, my bad. I put 0 in there. 0 squared is 0 plus 16. So when I plug in 0, I want to get out -4. When I put in 0, I get 16. Square root of 16 is 4. That means I need the -1. So the actual answer is the negative root. Box it in and put it up on our fridge. Okay, so this whole section is based on this little shortcut. So when we have exponential growth, the more things grow, so when you have exponential growth, let's say you have money in a bank account, right? The longer you leave that money in there, the bigger it grows each month. So if I leave $1 in there, the next month I come back, I'm going to have a little bit more. But then the next month I'm going to grow by a little even more because I had that, let's say, $1.10 in there now instead of $1. So now I'm going to grow by a percentage of $1.10, which is a bigger amount. And then I'm going to grow by, and the longer you leave it in, the growth gets bigger. Exponential decay, same idea. So I'm going to start losing. I have a lot. I'm going to lose a lot at the beginning, but the next time I have a little bit less. So my decay, my loss will be less each time. So quantities that grow or decrease by a factor or a percentage are exponential. They have this nice little relationship here. If dy dx is equal to k times y, then that's the equivalent of saying that the rate of change is directly proportional to that quantity. So this is our math way of saying that that's how an exponential function changes. Like, for instance, if I'm losing, how do I want to say it? Yeah. So how is my amount in the bank changing? This is what this would represent. The change in my money over time. Well, that would be some factor. Like, let's say I'm getting 1.03, 100. Let's say I'm getting 3% interest. So I would take that 1.03 and I would times it by how much money I had. Then I would take that new amount and I would times that by how much money I have. So this little relationship is this idea that if you have money in the bank and you're earning interest on it, however much money you have, it gets multiplied by whatever your interest factor is. I don't know if that was very helpful, but hopefully it made a little bit of sense. So we're going to now solve this for the general case, and you're going to see that there's a nice little shortcut that we're going to be able to apply over and over and over again for the rest of these notes. Solve the separable differential equation, dy. So I need to get, my two variables are dy and dt. So I need to get the y stuff on one side, the dt stuff on the other. So I'm going to bump this over. That means I have to divide by that. So I would have 1 over k times y dy. Then I'm going to bump the dt to the other side. Then I can integrate. Okay, so first of all, 1 over k is some constant. So I'm just going to take that constant out front. Times the integral of 1 over y is the natural log of absolute y. And then what's the integral of dt? Well, that's like saying 1 dt. So when I integrate 1, I would just get t. And then don't forget your plus c because we're in the general situation here. So this is still, we're trying to get the general, which means we need to get y by itself. So I'm going to multiply both sides by k. So I now have the natural log of absolute y equals k times t is kt. K times c is some new constant. I don't really care what it is. Who's keeping y? I'm going to e to the now. So this now looks like e to the natural log cancels, so we get absolute y equals e to the kt. I'm going to put it in parentheses, e to the kt plus c. This is something we talked about in the last lesson, so I'm going to break this apart, right? E to the something plus something else turns into a multiply. So absolute y equals e to the kt times e to the c. What's this? This is some number. E to some number is some other number. So I now have absolute y equals, I'm just going to call that new number my constant. And then here we are again. We can't leave this as absolute y. We want to solve for y. So whenever you want to get rid of an absolute value, you can do that as long as you put a plus or minus on the other side. And we talked about this before too. Plus or minus of a constant, we don't know if that constant is even positive or negative or anything. So we can roll that plus or minus in with the c, and we get this relationship, this general solution. So why is that helpful? Well, we don't want to have to do this every single time I get a problem where they tell me that the story is exponential. So we need to memorize something. We don't usually like to memorize. I'm with you. But if dy dt is equal to ky, which means that you have some sort of exponential relationship, then your equation is going to be some constant times e times another constant to the t, where these two k values are the same value. This is worth memorizing. I don't have you guys do a ton of memorizing in here, but this one is worth memorizing. All right, let's put it to use. So we've got a population of bacteria. It increases from 400 to 1,600 in 3 hours, assuming that the bacteria population grows according to the rate. Boom. So as soon as I see this, this is a dead giveaway. As soon as I see this, I know I'm going to be using, now I'm going to be using y equals big C e to the kt, which for us, I'm going to change the letters. So y is going to become p. P equals c e to the kt. You know what I mean? Instead of doing dy dt, we're using the letter p for population. Where t is time in hours. Ooh, you catch it on? You catch it on? What's this? These are units. That means I'm going to have units in my story. Or sorry, in my answers. My answers are going to need to have units because they gave units in the story. So find the value of k. So there's a number of different ways to do this. I go for the simplest route. So I want to figure out where this, they didn't tell me where the story started. C ends up being the equivalent of the initial condition, the initial population. They didn't tell us what the initial population was in this story. So you could pick your initial population to be anything you want, but I would recommend picking something that made sense for the hint that they gave us. They said that our culture grew from 400 to 600. That's a population change. And then they told us in 3 hours. This is a time change. So I can pick my initial condition to be 400. So I can say at time 0, remember my points are time and then the population. At time 0, what was the population? I'm going to say 400. And then 3 hours later, what was the population? 1,600. There we go. Now you got to kind of think these through. They're not going to be one of those problems where you can just always do what we did last time. You got to kind of think it out. All right, so let's try to put this together now. So let's first figure out what big C is. Now, I'm going to tell you that it's going to end up being 400 every single time, but let's just prove it. So population is 400 equal to, we don't know what big C is, e to the, we don't know what k is yet, but we do know that time is 0. All right, what's k times 0? 0. What's e to the first? 1. So therefore, 400 is equal to c. So now we know what c is. So I'm going to now take this and merge it with this to get us a little bit better of an equation. So we have population is equal to 400 e to the k times t. But the question was find the value of k. So what can we do to figure out, we've got this as our starter, what can we do to figure out this value of k? Well, I'm going to use the other point, and I'm going to plug that in for p and t to see what k would be. So I'm going to encourage you to try that on your own. See how you do. Pause it. All right, my population was 1,600. 400 e to the, we don't know what k is, but we know what t is. T is 3, so I'm going to go with 3k. Trying to solve for k, so farthest away is 400, connected by mult, division, so I get 4 equals e to the 3k. Who's keeping k? Who's farthest away? E to the, what kills e to the? Natural log, so I get natural log of 4 equals 3k. And then k is got to kill off the 3, So k is equal to 1/3 natural log of 4, which is the same as if you want to write it this way. Either one of those are equivalent statements. So it's up to you how you want to use it. So how fast is the population of the bacteria increasing when the population is 3,000? So let's look. This is talking about how fast. How fast. When we're talking about fastness, that's a rate of change. Did they give us a rate of change anywhere in this story? Hopefully, yeah, you highlighted this. This is a rate of change. That's slope, right? A derivative is the same as slope. So that's my rate of change. Can I use this to figure out what's happening when the population is 3,000? So what do we know when the population is 3,000? I know that my population, P, is 3,000. I want to figure out how fast the population is changing over time. That means I need to know, I know what the population is, I know how to plug that, I need to know what K is. Well, we just figured out what K was. So K is natural log of 4 over 3 times the population, which is 3,000, which ends up being 1,000 natural log of 4. Why don't I want to box that in yet? What's wrong with this answer? Now, maybe you want to try to clean it up, like you could bump that up there, 4 to the 1,000. I don't think that'd be a whole heck of a lot nicer. But there's something really big that you didn't write down yet that you would have to write down for points. Hopefully you caught it. Units. So this is the change in population over the change in time. So our population, I'm just going to call it bacteria. Over time, what's our time measured in? Hours. Don't forget your units. Remember that chapter 2 test? We had all those units on it. The amount, A, increases at a rate proportional to, boom, game over, man, game over. As soon as I see proportional, now they don't always give me this thing, the rate of change, but I think about it whenever I see things like proportional or changes directly with. So then the other formula would be, remember, it's y equals big C e to the kt. So for my story, it would be A equals C e to the kt. All right. We got units. Make sure you circle those. Be aware. Be ready. Units. So make sure that you're writing down some units. They want the exact and the decimal approximation. Okay, the amount triples every 11 hours. Find the value of K. So we first have to figure out some information. We got to make up some information on our story. Like I said before, if they don't tell you how the story begins, you can kind of pick whatever you want for your beginning. I'm going to choose my initial pop. Remember, we're talking about time and then the amount of things over time. So for a certain amount of time, there's a certain amount of, what are we even talking about? The amount, it's just the amount. Okay, whatever the amount is. So what time? I want to pick my initial time to be one of whatever these things are. I don't care what they are, but I'm going to pick that there's one of them. So it triples every 11 hours. So what's my new time 11 hours later, and how many of these things do I have now? 3. So I can start to figure out that these two things, this is going to be my initial condition. So my amount is going to be 1 e to the kt. They gave me, or we figured out because of the hint that it triples every 11 hours, that we have another point. So the amount is going to be 3 when the time is 11. So I can start to clean this up. 3 is equal to e to the 11k. Who's farthest away on the same side? E to the, so I'm going to natural log both sides. Who's keeping k from being by himself? 11. So natural log of 3. Boy, that was an easy one. That doesn't happen very often. Ooh, 3 decimal approximation. Calculator. Natural log of 3. Take that and divide it by 11. I got my decimal approximation to be 0.99. Dang it. 0.099. The weight of a population of bacteria is given by a differentiable function b of t, where blah, 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 blah. Okay, so right off the bat, as soon as I see something like this, I'm getting in the habit of trying to write myself this over and over until I can remember what that formula is, until I have that memorized. The sect, we could call it the sect formula. I don't know. Come up with something more clever over time, hopefully. Now I'm going to replace this y with a b eventually. Maybe I can just do that right now. Make that a b. Okay. The weight of the population is given by the differentiable function, where b is measured in tons. Circle these tons. Hours means we have units. Now, why didn't I have to write units here? Because they didn't actually ask me to find anything. They found the k value, which isn't part of the story. This is the factor at which this story is changing. It's not the amounts of amount, apparently, or hours. The weight of the bacteria population, according to the equation, where k is increases, so that was a rate. That makes sense. At time equals 0, that's a good one. So at time equals 0, the bacteria population weighs 3 tons. Jeez. And is increasing at a rate of 2/5 tons per hour. So it's increasing at a rate of, so wait, that's telling me we can use this right off the bat because that's another rate. So at time 0, the story is changing by 2/5. So I can go to this equation here. This is the rate of change. What did they say the rate of change was? They said it was 2/5. Well, let's do it this way. The rate of change is k times the population. So what's the weight of the population at time 0? 3. And then they said that that increases at a rate. I don't like the way I did that. So, I don't like the way I did any of this. I'm going to try again. Let's try this. So, D, change in bacteria over change in time is K times B, which means the change in bacteria, they told us, at time 0 was 2/5. K times the amount of bacteria at time 0 was 3. I'd divide both sides by 3. I would get K. Therefore, K is equal to 2/15. And then I just got to plug and chug into, yeah, because I already know. Can you write the equation now? Try to pause. This is, remember, C is the initial condition. If you want to go calculate it, you can. But if they ever give you the initial condition, that's what C is. That's the initial amount C is. So B of T would be equal to, well, what's our initial amount of bacteria? 3 tons. E to the, we said K was 2/15 times T. It even fit in that space. That's a new one. All right. We're rolling here. What do we have left? I think I'm going to try to do, let's finish this page. So we've got this radium. It loses its mass at a rate directly proportional. That's a clue. That's a hint. So directly proportional. That's telling me this dy over dt is equal to k times y. Therefore, y equals ce to the kt. Its half-life is 1590 years. So I'm going to circle that. That means I need to have units. If we start with the sample with the mass of 100, that's another clue. So if we start with the sample of 100, that means at time 0, I had 100 milligrams. I'm going to circle the milligrams too so I can keep track of those are my units. Find the formula for m of t that remains after. So that means I'm trying to take this equation. I'm trying to figure out what m would be. So that would be what? M of t is equal to my initial condition, which how much did we have to begin with? 100. E to the, we don't know what k is, and we don't know what t is. So we got to do some work. This is where we're going to begin. So they got to give us a hint somewhere along the way so we can figure out what that k value has to be. Well, what did they tell us about, what other thing have they given? They gave us the initial amount. We used that. They told us it was proportional, so we used that. What haven't we used yet? Well, obviously the fact that we've got a half-life of 1590 years. So I can use that as a specific case in this for this equation. So if I have 100 milligrams, after one half-life cycle, I would have how much left over? 50 would equal 100 e to the k. We don't know that, but how many years would it take for me to turn 100 milligrams into 50 milligrams? It'd take 1,590 years. So this is something that we can start to solve. So I'm going to bump over the 100, so I now have 1/2 e to the k. I'm going to write that as 1590k. Who's keeping e from being by himself? So we would need to do a little natural log action. So natural log of 1/2 equals, oh, I forgot the k, 1590k. And I'm actually going to write this one as 1 over this, I think. Let's see how nasty this looks. 1 over 1590 natural log of 1/2. That's what's equal to k. Notice I'm not boxing in that because that's not my k, that's not the answer, is finding the k value. I'm going to now take that and plug it in. I'm trying to come up with an equation for m of t. So m of t would be equal to 100 e to the, our k is, oh my goodness. Oh, I got to squeeze this in there. 1 over 1590 times the natural log of 1/2 times t. Oh boy. Right? That's my k. So all that stuff that we found for k gets stuffed in there for k, and then you got to have the t at the end. How many milligrams of the original sample remain after 100 years? And that's just some plugging and a chugging. So if this is my function, I would start to calculate. So that would be m of how many years? 100 equals 100 e to the 1 over 1590 times natural log of 1/2 times t, which would be 100 again. Not something I would expect you to do in your head. I would recommend going to your calculator, hitting pause first to see if you can do this without me telling you the answer. I got 95.734. Do you have units here? Yes, this is milligrams. Don't forget your units because this is an actual amount. By the way, if this is a free response, you could just stop here, but you would still need to write milligrams after that. So you don't have to clean it up if it's free response, especially this one. You're not going to use that answer again. So there's really no time, no reason to waste your time cleaning that up. How many years, the exact answer, will it take for the sample to only have 3 milligrams remaining? So if this is my function that measures how much the mass of our radium-226 is, I need to figure out when that mass is equal to 3. So let's plug and chug. 3 equals 100. E to the 1 over 1590 times the natural log of 1/2 times t. This one's all about your algebra and how well you know how to clean stuff up, because this would not be a free response, I don't think. I think this would be a multiple choice. So I would start off by dividing. So I would get 3 over 100 equals e to the 1 over 1590 natural log of 1/2 times t. Next farthest away is e, so I would natural log both sides. So that's the natural log of 3 over 100. So I natural log this, so that canceled out, so that's a little bit nicer. 1590 natural log of 1/2 times t. I'm running out of room, so I'm going to do a little arrow to show where I'm moving. I got to times both sides by 1590 now, so that would be 1590 natural log of 3 over 10 is equal to natural log of 1/2 times t. I don't like the way I did that. I'm going to change that to here and here. Natural log of 1/2. So that's just a scribble. How is natural log of 1/2 connected to t? By mult, so I would divige. So now we have, I'm going to try it this way. T equals 1590 natural log of 3/10 over natural log of 1/2. Now, I would be more than happy with that answer if I would actually probably tell you just type it in the calculator. But if this was a multiple choice, they would try to clean this sucker up. So let's see if there's some different ways that we could clean this up. So I've got natural log of things getting divided. So one thing I can do is I can separate this. Natural log of stuff divided. You should be able to clean that up. Now I need to group it. So how does this break apart? Hopefully you did natural log of 3 minus natural log of 10. Remember, if you're natural logging something divige, you can bust them into their own with a subtract. Now I could do the same thing on the bottom, or how else can we think of 1/2? We can think of 1/2 as 2 to the negative 1, right? 1/2 is the same as 2 to the negative 1. And then I could bust that negative out front, and I would have negative natural log of 2, which is a lot nicer looking answer. Now, maybe that would be the best they would clean it up. I doubt it. I think they would still do one more thing. I think they'd take that negative off the bottom and they'd put it to the top. But then they'd be even extra sneaky. They wouldn't leave it here. They would take it and distribute that negative in here. So I think this is what the final full credit answer would look like. They took that negative, they gave it to the 1590, then they took the 1590, the negative from there, and distributed it, which made this piece negative and made this piece positive. So I'm going to stop here. I would encourage you to maybe attack the homework before you watch the next video, or, I mean, it's up to you, but putting off that homework is not going to, it gets overwhelming if you wait too long.